Yeah, today we will be discussing about stick-free neutral point. You have already done how to find a stick-fixed neutral point through elevator deflection, right? We will be talking about stick-free neutral point, and before we talk about the experiment, let us recapitulate what is a stick-free neutral point and how it is different from a stick-fixed neutral point and what is the relevance of it. Okay? Please understand, if I see Cm versus alpha or CL graph, it is something like this, right? And this point is the trim point. No issues? Now, suppose you want to fly at this CL. The CL1, you want to fly here. So, what is the action the pilot should do? So, you know, from the static stability of the airplane, the moment you try to change the CL, that means you want to change the angle of attack, then it will automatically generate a negative moment because it is statically stable, right? So, it will have a tendency to come back to this original CL at which it was flying. Just to give you a scenario, suppose I am flying at an altitude, let us say 1 kilometer, flying at a CL 0.2 at a speed V1. So, say CL 0.2 and V, let us say, is 100 meter per second. Let us say that point is this. This corresponds to CL equal to 0.2 and V equal to 100 meter per second. When I am saying, say the pilot desires to fly at a new CL, which is CL1, let us say now pilot wants to fly at CL equal to 0.3, and if he has to maintain a level flight at the same altitude, so he has to do what? Reduce the speed, number one, and also the elevator deflection, he has to do something, right? Because why he has to reduce the speed? Because he will be flying at same altitude. Now, the moment I increase CL to 0.3, the lift will become more than the weight, because lift is equal to half rho V square SCL. If I am increasing the CL and this is equal to W, if I am increasing this CL, then this half rho V square SCL will increase unless and until it reduces the speed. So, he has to reduce the speed. So, that means what is happening? He is going at some angle which corresponds to CL of 0.2. He is now increasing the CL to 0.3 by raising the angle of attack, but then he has to also throttle back, reduce the speed. Otherwise, it will start climbing. Okay? And you also know that if I want to fly at this CL1, it will generate a negative moment. So, I have to generate a positive moment by giving elevator deflection, right? And that is why if you see this graph, delta E versus CL trim for a given CG location, XG1, you have definite value of elevator deflection required if you want to fly at this CL, at this CL, at this CL, or at this CL. You have different value of delta A required. So, the pilot, if he wants to fly the airplane at different CL, how should I develop field for him? He needs to develop a field. How will he fly? So, one way is you make a chart, delta E and CL, or CL means you can always relate to speed by giving density, and he sees that chart, oh, this much of V, I will put this much of delta A, this much of V, I will put this much of delta A. Or sometime you know that for giving delta A there may be a rotating shaft, a wheel, he can rotate this, many combinations were there. The basic understanding is you are developing the field of the airplane for the pilot through delta E and the speed. So, he develops field, this much altitude, this much speed, this much elevator deflection I will get. But that may not be a very good way of giving him a field, right? For example, if you are driving a motorcycle, if for every speed there is a marking, put this mark, it will take this much of speed, put this mark, this will give this much of speed. Do you think that is a correct way of getting a feel? How do you get a feel when you are driving a scooter? As you accelerate, you get that torque, right? and then you know, as getting more and more torque, you are getting the field for the airplane, a certain field for the motorcycle, and then reduce. That is how you get the field. Okay. For airplane also, what is done, if I somehow can give the field to the pilot in terms of stick force, right? If he wants to reduce the speed, he pulls it like this. If you want to increase the speed, he pushes like this, right? And this field of the force or the gradient will help him in getting the field for the airplane, right? And that is where you need to define something called stick force. And you need to use that concept of stick force to define a stick-free neutral point. Okay? But be very clear, if you see my the module, the airplane has only neutral point, right? It is stick-free neutral point we are defining so as to develop a mathematical model which will help to give a feel for the pilot. That's all. Okay. So now the question is, we want to find out the stick-free neutral point through the experiment. If you see the expression for a stick force, you have to again refer my lectures or any textbook. From there, you can easily see that dFs by Q bar is the dynamic pressure, by dCl equal to 0, and stick-free neutral point is defined as xCG location at which dFs by Q bar by dCl is equal to 0. This is the definition, or this is the mathematical backup to determine the Nm bar or N naught bar, repeat, N naught bar, stick-free neutral point, and generally for stick-free we put a hash here. For a stick-free we don't put it here, right? So how do I find stick-free neutral point? I need to find that CG location at which dFs by Q bar by dCl is equal to 0, right? If I understand this, then let's see how do I do experiment. First question comes, how do I measure stick force? You know, this is basically based on strain gauge. You have the stick, let's say stick like this. The strain gauges are on the stick. So as I pull it, so there will be a bending, there will be stress developed, and from that, through the strain gauge measurement, I can find out how much the forces have been applied in terms of pull or a push, right? So you use a strain gauge principle. You also use Wheaton bridge. That is what, through strain gauge, we measure the stick force. And now, if I want to conduct an experiment to find out a stick-free neutral point, then what I do? I go for a cruise, right? And again, I look for altitude. I note down the altitude. I note down the outside air temperature, right? Then, for different V, let's say V1 I am cruising, you note down what is the stick force. Then again for V2, V3, V4, you note down all those stick force, what are being applied. So you just need these two measurements. So you know what is the stick force. For dynamic pressure, how will you calculate dynamic pressure? What information you require for this? Half rho V square, right? How will you get rho density? Through outside air temperature and the standard table. How do you get V? Airspeed indicator, then you correct it for true airspeed, right? So all the information available, but we need to also find out CL because I want to see the change, this gradient with respect to CL. So for CL, what additional information I should have? The weight of the airplane, right? So you will also measure, which you are doing anyway, weight of the airplane. You can take the average weight during the cruise, you can take the initial weight, final weight, average or takeoff weight, then landing weight, take the average, or you carry a stopwatch, see how much time it was not cruising or how much time it was cruising. So you can, the fuel consumption rate, so you can find out the average weight. That is your choice. So once you have this V and Fs, and you can easily calculate what is CL. CL will be 2W by S by rho V square. Correct? No issues because you are cruising. But this experiment will be done corresponding to a XCG location. That is, there will be few students and the pilot flying, which corresponds to a given CG location. So this should be repeated for different CG locations. So you can always manipulate the weight of the passenger, and fuel weight we can go on changing, so that I can generate this sort of a data for n number of CG locations. Let's say from XCG1 to XCG5, 5 set points we generate. That means I have this measurement corresponding to a XCG configuration. Then another batch goes, he generates this experiment. Again, that data corresponds to XCG2, XCG3, XCG4, XCG5. So what do we have now? What we will have? Fs. You can always plot Fs by Q bar. So you can put another column here, and you can calculate what is the value of Q bar equal to half rho V square. So this information is available to you. Then you plot Fs by Q versus CL. Let's say different speed. Let's say they look like this. This is for XCG1. Similarly, there could be another for XCG2. Similarly, for another XCG3. Like that, you can have n number of points. Right? Up to this point is clear? Now, what is our aim? Our aim is to see what is that CG location for which dFs by Q bar by dCl equal to 0. That CG location at which dFs by Q by dCl is 0 is called stick-free neutral point. Right? Now, what I should do? I should plot from this data. I put it here XCG bar, and here I put dFs by Q bar by dCl, which essentially means the slope of this line, isn't it? Right? Now you have to plot dFs by Q by dCl versus XCG, and you take one graph XCG1, take the slope is negative, this is this point. For the second one you take this, third one you take this, and then you join by a straight line, and this point is what? This is the XCG location at which dFs by Q by dCl is 0. So this becomes your stick-free neutral point. Clear? You can cross-check with stick-fixed neutral point. Earlier we did, that was d delta E by dCl versus XCG, and the XCG location at which d delta E by dCl was 0. Right? So this is the way to do stick-free experiment to find out a stick-free neutral point. So I will just write the revised table. So this is, you are having an altitude, you note down outside air temperature, you note down the weight, then fly at different V, so V1, V2, V3, V4, like that, and measure stick force, 1, 2, 3, 4, 5. You also find Q bar, which is equal to half rho V square. You calculate CL, 2W by S by rho V square. Then you find out dFs by Q by dCl, and this should be for different CG locations, right? XCG1, 2, 3, cross plot, you will get these values. So this table will correspond to one CG location, XCG1. Similar table will be there for another configuration, XCG2. Similar table will be there for XCG3. So you have to pick up the slopes and cross plot with respect to CG and see where, after extrapolating this point, where this line cuts, that is your stick-free neutral point. As simple as that. Okay, clear? Now, to end this part, we will also see how to find a stick-free maneuvering point. Neutral point is over. So, we will do like you have a stick-fixed neutral point, you have a stick-free neutral point. For a stick-free neutral point, we are talking in terms of stick force, right? Similarly, stick-free maneuvering point, we will be talking in terms of, again, stick force. What was stick-fixed neutral point? What was the condition? For stick-fixed, which we did earlier, stick-fixed neutral point, Nm bar, was defined as xcg location at which d delta E by dn is equal to 0. Isn't it? That is how we did. Now, if we look for stick-free maneuvering point, stick-free Nm bar prime, so that is the xcg location at which dfs by dn equal to 0. What is n here? Is a load factor. So, what sort of an experiment we do? We do not go for a pull-up maneuver. What we do? We go for a turn, steady coordinated turn like this, and you turn like this. And same time we maintain that it doesn't lose the height. Right? That is, if I draw the diagram here, if you see, when the airplane was not having any bank, and if this was the lift, then the lift was balancing the weight. That is how it is not losing the height. Now, suppose if I bank it like this, what will happen now? Now, the component of lift will try to balance the weight. Say L cos phi will try to balance the weight. So, if the lift was same, then it would not be able to balance the weight. It will start sinking, right? Okay. But when we do this maneuver, we ensure that altitude is same. It is steady coordinated turn. That means for that to happen, you could see I have to ensure that L cos phi is able to balance the weight. The component of lift should be able to balance the weight. So, here I could see L by W equal to 1 by cos phi. And what is L by W? Load factor. So, N. So, I know N equal to 1 by cos phi. So, if the pilot is flying the machine and taking a bank of 45 degree and making a steady coordinated turn, so what is the load factor you are experiencing? Let us say 30 degree, then 1 by cos 30, right? Okay. If it is 60 degree, then load factor of 2. It's a very large number, right? Okay. Don't underestimate load factor of 2. So, this is to tell you how we generate this n, because we have to find out a condition wherefrom I can extrapolate to get the CG location for which dfs by dn becomes 0. Then it will be a stick-free maneuvering point, right? So, what do we do? Again, we do experiment. We go and note down altitude, outside air temperature, and then weight. Then the pilot goes for a steady coordinated turn at different speed, right? So, he does that 1, 2, 3, 4, 5, 6, 7, 8. Each time we measure what is the stick force applied. This is the only measurement required. Bank angle you get from the turn bank indicator, a stick force you will get from the strain gauge based stick, V from the airspeed indicator, and it goes without saying, you know that that speed is the equivalent airspeed, so you have to correct it for a true airspeed by using the relationship. So once I have this, now you see what I will do. I will simply again conduct this experiment for a given XCG, let's say XCG1 configuration. So then I will plot Fs versus n. And how will I get the value of n? N I will get from here, n equal to 1 by cos phi. Right? So I get the value of n. So I plot Fs by n, and let's say these values for different speed. Again, this is say XCG1. Similarly, I get for another XCG2. Similarly, I can get for another XCG3. Like this. You can go on generating. Once I do this, then what is the next step? You should be smart enough to now tell me, how do I get a stick-free maneuvering point? I will do cross plot between XCG and here dfs by n. What is dfs by n? For a given XCG location, let's say XCG1, what is dfs by n? That is the slope of this line. Right? So I pick XCG1 and then whatever slope, I note it down here. Similarly for XCG2, I again do this, XCG3, like that, few points I'll get. I'll try to fit it through best fit. And what is this point? This will be? That will be a stick-free maneuvering point. Is this understanding clear? Any doubt anybody having? Okay, thank you.